Measuring and calculating the ohmic stuff is easy. Your voltages, currents, resistances, and power, even AC versus DC. But what about the more exotic non-ohmic stuff like capacitors and inductors? It's a little trickier. So first let me say, if you want to measure a capacitor for actual work and you need an accurate answer, go get a multimeter that has a capacitance measurement mode. I've seen them on the shelf. They're not going to be exotic pieces of equipment. So use the right tool for the right job. But if you just want to do it for fun and learning like me, there's many different ways. The most straightforward way is you make a circuit that you know how it behaves, like a low-pass filter or some sort of oscillator or timer, and you assemble it where all the components are known except for one capacitor. You measure the output, such as with an oscilloscope, examine the timings, and calculate backwards to find the capacitance. That works fine. But I had thought, once I discovered the formula for the energy of a capacitor, why can't I just use that? And then researching this and trying it, I discovered the two capacitor paradox. Feel free to look up that video. It's just called two capacitor paradox, charge sharing. I discovered that little issue and it led me to this. So now I do have a method where you don't need any tools. You don't need an oscilloscope or anything. You just need a multimeter, an op-amp, other capacitors, just normal stuff you're going to have. So how does it work? So the idea behind capacitors in parallel is that they conceptually share the surface area of their plates as if they were just a larger capacitor. So you add the capacitances and you have this parallel part behave as if it was one bigger capacitor. The equalization over them, if they have a different voltage on them, it equalizes based on charge over the surface area. I go into more detail on this in the two capacitor paradox video, so watch that. Here I'll do a quick review. You have a power supply. We'll call this V supply. You have a capacitor of a known capacitance we'll just call capacitor 1. All of these are tied together with a common circuit ground, and then you charge capacitor 1. This one, we'll call it capacitor X because we don't know the capacitance. This is the one we want to know. This one is uncharged, so we fully charge this one. That one is completely uncharged. And then we switch the wiring to that. And these equalize so that they both have the same voltage, which means that the charge across the capacitance, the conceptual shared capacitance of them sharing their plates, it equalizes over the surface area. So all the surface area has the same amount of charge per surface area. So if this one is 1 farad and this one is half a farad, then this one will end up with 2/3 of the charge, the electron separation, and this one will end up with 1/3, because this one will be 2/3 of the total capacitance and this will be 1/3 of the total capacitance. So at that point, all you have to do is measure the new voltage. We'll call that one VE, the voltage it equalizes to. And then we have math that we can just reverse calculate to figure out what this capacitor value is. Now, how do we measure this? Well, you can't just stick a voltmeter on there, as much as I'd like to, because even if it has a very high input impedance, it's still going to be only in the mega ohms range, which is a lot when you're talking about measuring a circuit that's live and trying not to disturb it. But a mega ohm is still going to put through a fair bit of current, which is going to drain the capacitor you're measuring. Especially if the capacitors are small, you're trying to measure picofarads, the multimeter is going to drain them fast. They're going to lose volts per second. So you could measure it with an oscilloscope. That's going to measure it fast. It's going to drain it, but it's going to get that first measurement real quick. And then, it'll drain it, but you'll have the first measurement and you'll know what the value was. But we can also just buffer it. So here's my test setup. I have the unknown capacitor, and I have a momentary switch here, which can be a button, or in my case, just plugging and unplugging the breadboard wire, connecting both ends of the capacitor to ground, so this will always drain the unknown capacitor in between tests. So I just hold down this button, or plug in the connection, whatever, and it'll drain this capacitor down to 0. Then I've got the known capacitor and the supply voltage with this momentary switch, so that I can press this switch down and it will fully charge this capacitor without doing anything to this capacitor, because this one's got another momentary switch. And then once I let that go, it's disconnected from the power supply and I press this one, and that shares the charge between the two capacitors. And then what I've got over here is it's reading the charge shared between both of these capacitors. It's buffered into an op-amp, and an op-amp has an immense amount of input impedance. It still has some current draw. It has an input bias current. So you do have to be fast for an accurate result, but you don't have to be instantaneous. You have seconds, especially if you're measuring entire, decivolts or whatever. You can hold it down for a good few seconds and the number's not going to change because the current is so small. So the op-amp is in a simple unity gain non-inverting input configuration. So the voltage goes into the non-inverting input, its own output goes into the inverting input, so that it equalizes them, and the output equals the input, the non-inverting input, which goes into the voltmeter. So the process is hold down this button to drain the unknown capacitor, then hold down this button to charge the known capacitor, then hold down this button to share the charges. And you can easily swap in and out these capacitors and just press the buttons to do test after test. It's real neat. Now you might say that you have to hold this button down to accurately measure VE, the equalized voltage, but that's only while it's equalizing. Once it's equalizing, they're both the same voltage. So once you let go of the button, then this voltage is this voltage as long as you measure quickly. So it doesn't matter. So you just put in the capacitors you want to measure, turn on your power, press this button for a bit, then press this button for a bit, then press this button for a bit, and look at what your voltmeter says. Nice and easy. It's really cool. So the input impedance of the voltmeter is completely irrelevant because it's being driven with the power supply of the op-amp. The only thing that matters is the input impedance of the op-amp, which is nice and high. And since we know the supply voltage, we know this capacitance, and we know, of course, VE because we measure it, the only unknown is the capacitance of the other capacitor, and we can just do the math. Let me go quickly over the math once again. The energy in a capacitor equals 1/2 times the charge times the voltage, and it also equals 1/2 times the capacitance times the voltage squared. Again, watch the two capacitor paradox video for a better explanation of this, as well as the video about energy in a capacitor. I assume that's what I called it. So what's being shared is charge, not energy. But we don't need energy anymore because we just know these are equal. So all I need to do is solve for charge. So charge equals, the halves cancel, one of the voltages cancels, and we get the charge equals the capacitance times the voltage. Let's write this up here. So we know that the charge of the full system, which is the charge on the first capacitor, the one we charged, equals the capacitance of the first capacitor times the voltage supply that we charged it to. But the charge doesn't go anywhere when we put in the uncharged capacitor and it equalizes over the surfaces. When it equalizes between the known and unknown capacitor, the charge doesn't go anywhere, it just spreads. So the amount is the same. So now we've got capacitor 1 plus capacitor unknown times the voltage that it equilibrated to, because parallel capacitors just share their capacitance. And this is the voltage we measured, and we know the capacitance because we look on the label, what's the capacitance? We don't know that, but we also don't know the charge. So now we can solve for the unknown capacitance because we don't need this charge anymore. We just know these are equal. So we want to isolate the unknown capacitance. So we can divide over the voltage we measure, and we can subtract the known capacitance and get just the unknown on the bottom. So if you write that out, the unknown capacitance is, and we can factor this out, so C1 here, C1 here. So if we do this, then this becomes -1. So the known capacitance times the ratio of the original voltage to the equalized voltage that we measure, -1. And that is the capacitance of the unknown capacitor. Now, in testing this, of course, the voltage that I actually measure is not the voltage that it's supposed to be, because the known capacitor has a variance. All capacitors have a variance, all components have a variance. So when you get a capacitor that says it's 6.8 microfarads, that's plus or minus 5%, 10%, 15%, whatever. So you do these calculations and you're going to get an error because you didn't actually technically fully measure the known capacitor. You're going by what it should be, and that's your error. So what I'd like to do is calculate the voltage I would expect if there was no variance. If 6.8 microfarads meant 6.8 microfarads, and I want to compare the measurement voltage I get to the voltage I would expect. So to do that, we can just solve back around, because this time we know the capacitance of this, because it's also, I'm testing with capacitors I know. I'm just testing this method. So what we don't know, what we want to find is the voltage we expect it to equalize to if these capacitances were exact. So we'll multiply this back out, minus C1. So then over here, Cx. So I'll add the C1 back over here. I'll divide by the C1. So now we have that kind of ratio. And now I'm going to flip them over. So we get the equalized voltage over the supply voltage is the known over the unknown plus the known. So I just flipped them over. And now we can bring the supply voltage over. And if we assume we know both capacitances and the supply voltage, we can figure out what voltage they should equalize to, what voltage we should measure, if these capacitors were actually exactly the values they're supposed to be. So these are the two formulas we use. If we're trying to find an unknown capacitance, we do this and measure the equalized voltage. And if we're testing to see how accurate everything is, maybe we're testing the variances of the capacitors to see just how good or bad it is, then we know the capacitances based on what it says on the little flap, what they should be, and then we find what the voltage should be when we measure. So I did some of these tests, and I'm going to put up a little chart real quick and show you my results. For the known capacitor, I always used 6.8 microfarads, and I used the same one. So, of course, it's not 6.8 microfarads because there is a variance. But I used exactly the same capacitor for every measurement, so whatever the true value is, the true value was not changing between measurements. For the unknown capacitor, I used a 6.8 microfarad, a 4.7 microfarad, a 680 nanofarad, a 68 nanofarad, and a 6.8 nanofarad. For each of the unknown capacitor values, these are all from the same kit, so they should have the same variance. I don't remember what it is when I bought it. It's probably 5, 10, 15, 20%, somewhere in there. It's not that great, because it's just a cheap little kit, but the variances will all be the same because they're all from the same kit. But I measured several different capacitors of the same value and averaged the voltages I got to try and, narrow down what the average result was. And then the known capacitor I never changed. So the results I got for each of these, for the voltage they equalized to, I got an average of 2.67 volts. Oh, I should mention the supply. That would be important. Supply voltage was 6 volts. I guess that would be important, wouldn't it? I used a 6 volt supply. So they equalized to 2.67 volts there. So you can already see the variance because it should have been 3. Because the capacitors are the same capacitance, so they should have shared the charge equally, so they should share the voltage equally. They should equalize to be half the supply voltage. So 2.67 is reasonably close to 3, but anyway, like I said, that's the variances at work. For this one, I got an average of 3.21 volts, 5.13 volts, 5.90 volts, and 6.00 volts. The first thing you'll notice is that this is not a useful result. Basically, the second capacitor took no charge. 6.8 nanofarads versus 6.8 microfarads is a factor of 1,000. And you'll notice I'm only measuring to 2 decimal places on a cheap multimeter. So when you look at 5.90, you can see that there should be a lot more decimal places and there's a lot of detail being lost, and this will come to bite us in a moment. But we can immediately see that we can't measure 6.8 nanofarads with this setup. We need a more sensitive voltmeter to be able to do it. We need better equipment. I would use my oscilloscope, but anyway. So I then calculated the expected values if these capacitances were exact based on how I've got it set up, based on a variance of 0%. What voltage would I expect them to equalize to? This one, of course, is 3.00 volts. We would expect 3.54 volts there, 5.45, 5.94, and 5.99. And if we calculate the percentage error between the actual and expected, we get an error of 12%, 10%, 6%, 1%, and 0%. So the first thing to point out is, let's look at the worst error I got with equal value capacitors. It's only 12%. That's pretty good, and I could believe that about 12% is my variance, 10-15% variance in the capacitors. So, we're in the right ballpark, but why is the error going down? We already established that the higher the voltage gets, the more we're losing by restricted decimal points. Why is the error going down? Because the expected voltage is being calculated with fewer decimal decimal points as well. And I'm not talking about significant figures, that's just a hack, but you know there's something called error bars in physics. Basically, the error bars on the calculations, I'm not getting an exact expected value here, because you couldn't compare it. I have to compare roughly the same magnitude of error on both of these, otherwise I'm just inventing, because if I take this to 7, 8, 9 decimal places, then I'm just inventing accuracy over here. I haven't measured zeros. I can add zeros, but I haven't measured them, so, you know, this is rounded off. This is my multimeter rounding, so I need to round similarly. So that's why the error is going down, because all of the detail is being obliterated by the rounding, so I'm getting no error. So you can see that obviously this result is completely useless. This result is basically useless because it's so close. But you can still see that it's working. The point is, with all this crappy setup and on a breadboard and everything, it's working, even with all these errors. So let's dump these results. And now let me use my other formula. Based on the voltage I measured, what is the capacitance, the unknown capacitance? Well, here's what they should be. What did I actually get? Over here, for this one, I would expect 8.48 microfarads, which is a 25% error. Here I would expect 5.9 microfarads, which is also a variance of about 25%. And once I get down into the nanofarads, according to the voltage I measured, I have a 1.15 microfarad, in other words, 1,150 nanofarad capacitor, an error of 69%. Not so nice. So when the error on the voltages was around 10%, why am I getting these crazy errors over here? Because the errors are compounding by doing math on them. When you measure the voltage, you've got a variance in one capacitor, a variance in the other capacitor. We're assuming that the actual losses, like the input bias of the op-amp, the input bias current, is minimal. The losses to resistances of wires is minimal. My power supply is reasonably accurate. All those losses are small enough that we ignore them until we get down to like the small single-digit nanofarads, at which point you need better equipment. I would be using my oscilloscope instead of a multimeter. But you're really only dealing with the variances of the capacitors. And you're just calculating using those variances, and that's why we're getting that error that's within the capacitor variance. But then I'm assuming, in order to get the expected voltage, remember we assumed the value of the unknown capacitor. So you've got variance in this capacitor, variance in this capacitor, and then I took this voltage, which already has these errors in it. The variances of the capacitors is already in the voltage I measured. So how do these errors compound? When I'm measuring the voltage they equalize to, it's really only the two variances of the capacitors that are at work. But then I calculate the expected value of the capacitor from that. So I take this value that I measured and I assume that it is correct. I'm basically deleting the variances and I'm assuming these values are exact. So I calculate the capacitance from that. And then I calculate with these values again. I add in C1 to the equation again. So I'm taking the same error and I'm introducing it into the calculation multiple times. Every time I use a value that has error and I use it again, it compounds the error, and I use another one that has error and it compounds the error. So that's why these errors are so much higher, because every time you have an error bar, you know, it's like x plus or minus y would be how you'd represent a value, a measurement with an error. So if one measurement had an error of a 1/16 of an inch and another one had a measurement error of a 1/16 of an inch, and you used both, then you're going to have an error of 1/8 of an inch, a possible variance of the actual result. And remember, there's also rounding. My multimeter is rounding. These values are rounded, so even the rounding invokes error. And then that's compounding as well, because I'm using rounded values in the calculation, so that's why it's off. So I just wanted to explain why it's like 69%. This doesn't work. Yeah, it does. It's a proof of concept. Look at the order of magnitude, though. 6.8 micro, 8.48 micro. Yeah, that's off by a lot, but it's still kind of there. 4.7 to 5.9. 0.68 to 1.15. Capacitors generally come in only certain values. You're not going to have a 6.8, a 6.9, a 7.0. So if you look at 8.48 microfarads, the nearest value in my kit is 6.8 microfarads. So you could easily say, well, it's probably a 6.8 microfarad. And then you could, further measure it and say, oh yeah, it definitely is. You could also do a lot of trials if you were trying to measure the variance of capacitors in a kit. Let's say you wanted to do all this to figure out how bad your capacitors are. Use multiple of these and multiple of these, and use statistical analysis, standard deviation and all that stuff. You can figure out a trustworthy value, which is what they would write on the label of the bag, in this case like 6.8 microfarads. So you could test them, do enough results and plot them and figure out, oh, this is the variance of this set of capacitors. If you wanted to see, is your manufacturer telling you the truth, that kind of thing. But mostly I wanted to do this as a proof of concept, and the concept has been proved. The math works. So if you have good enough parts, you can measure capacitance with no tools whatsoever, at least to a certain accuracy. So I had fun and I learned. Mission accomplished. So for now, I'll be seeing you.